Hello everybody, I'm presenting challenges in multiphysics modeling of dual-band Mercatel infrared detectors. In this short presentation, I'm going to show some examples of simulation methods and the results obtained concerning dual-band infrared detectors. Multispectral capability across infrared bands is a central requirement for third-generation infrared photodetectors based on focal plane arrays of pixels, and Mercatel is a very versatile material for this. A typical dual-band detector is a heterostructure, in short made by two photodiodes connected back-to-back, each with a different band gap. The simulation scheme is shown here, and it is quite standard. Nevertheless, the presence of layers with compositional grading made quite challenging the FDTD approach. It must also be noticed that an independent simulation for each wavelength is needed. As a first step, we checked our modeling setup against this example coming from the literature, a two-color detector operating in the mid-infrared band. The idea was to simulate the response to a narrow monochromatic Gaussian beam focused on the central pixel. And we obtained a quite satisfactory agreement between simulated and measured responsivity spectra as shown on the right. Satisfied with this, we considered a mid-long infrared dual-band detector modifying conveniently the Mercatel composition profile. And on the right, the simulated quantum efficiency spectrum is shown for the two polarizations, and we can observe good spectral selectivity with low voltage. For clarity, I also marked in green the operating wavelength windows for an hypothetical detector based on this scheme. A concept of central importance for focal plane pixel arrays is the interpixel crosstalk. In few words, the crosstalk is the signal detected by a lateral pixel when only the central one is illuminated. The total crosstalk is given by the ratio of the photocurrent in the neighboring pixel and in the central one, whereas the optical crosstalk is the ratio between the two photogeneration rates. And the total crosstalk includes also the effect of carrier lateral diffusion. And this plot is the result. We see that optical crosstalk, black dots, dominates in both mid and long wavelength bands. In fact, the total crosstalk is superposed to the optical one. Moreover, optical crosstalk grows fast with increasing wavelength. Only left to the mid-wavelength band, there is a large component coming from diffusion, but this is not very important since both crosstalks are very low in the two windows of interest. However, we may ask, is it possible to reduce trench depth between pixels? And moreover, is it possible to reduce the optical crosstalk by changing the pixel sidewall angle? Let's compare what happens reducing the trench depth considering these four cases. The case A is the reference one. But it seems this is not a good idea. Even for a small reduction of the trench depth, the lateral carrier diffusion makes the crosstalk to go fast. Therefore, deep trenches seem to be mandatory. The other question was trying to increase the pixel sidewall angle in order to favor the effect of multiple internal reflections into the pixels. The only effect on the quantum efficiency spectrum is to obtain a more wavy spectrum, so this is not an interesting effect. Instead, the effect on the optical crosstalk is more interesting. In the long wavelength side of the spectrum, we observe a crosstalk reduction by a factor of 2. So this result could be interesting, and it is worth of an optimization and a deeper investigation in the near future. These are the conclusions, and thanks everybody for your attention.